Hey guys, Professor Floyd, and we are plowing through homework 10, and this is problem number 3. This is OEH 5723. So we are still applying Bernoulli's equation in different ways, and here we're basically familiarizing you with why we use manometers or incline manometers, and we'll talk about the pressure inside a duct as being 5 inches water gauge, or 3.2 inches or millimeters of mercury. And so it's like, why are we using those kinds of units? Because they have, through the Bernoulli equation, they have direct bearing on pressure. And so this is how we know how much the pressure is. So let's consider a situation where we just have a duct or some sort of flow vessel like a duct or a pipe, and we measure the pressure here and here, where there's no difference between the conditions at point 1 and point 2. So pressure 1 equals pressure 2, and if we have liquid in this manometer, then the height of the liquid will be the same. So I don't know if they look exactly the same up there, but they're supposed to be the same. So the delta Z, change in elevation, is 0. So if we then consider maybe we have a constriction, sort of like on number 1 where we have our hose and then we constrict it down, that might be what we have here, or we have a duct, a main duct that goes to a trunk line, and we want to accelerate that trunk, or maybe we're running it up a stack. We want to increase our effective stack height, whatever. So we decrease our diameter, which makes everything speed up, which drops our pressure. We calculated that previously too. So the pressure here is lower than the pressure here. So, or the pressure here is greater. So if you put a liquid that's connected to both of these, instead of it being at equal heights, you're going to have pushing, and you're going to have pulling. And that's going to be equal to the difference in pressure. And so we do this all the time when we measure ducts, and we want to know what's the static pressure in that duct. Oftentimes, though, we'll just measure it in reference to air. So we'll just measure the static pressure, and pressure 1 is going to be atmospheric. So it's how many inches of water is it above atmospheric pressure. So we have a delta Z. Suppose we have a delta Z of 4.2 inches. Now, suppose we have mercury in our manometer. So, barometers were originally water, and then the column was just so tall that it was unruly to handle some sort of column that tall. And so they found more I guess it was Torricelli, but I'm not quite sure. I'm not sure who it was. I think it was Torricelli, proved that the height was due to barometric pressure and not to the density of the liquid. And so he started getting more and more dense liquids and making a barometer that was more compact. Well, they started using mercury. And torr is also equal to millimeters of mercury. So 1 torr equals 1 millimeter of mercury. And that's the height, or that's the amount of pressure that it takes to displace a height of 1 millimeter of mercury. So this is basically just hydrostatic pressure. So we have our delta P is going to be equal to our 1/2 rho G delta Z. Let me just make sure that I'm not getting my equations mixed up. Hydrostatic pressure. Oh, yeah, no 1/2, sorry. It's just rho G delta Z, right. So the density, the force of gravity, and the height. So we're assuming that the cross section stays constant. So we don't need the volume, we just need the density. So in mercury, our pressure, our density is 13.55 times that of water. And water is 1,000 kilograms per cubic meter. I guess I should have started this a little further over. So our delta P equals rho G delta Z. So our hydrostatic pressure, or mercury, what's the I can't come up with one off the top of my head. So would be 13.55 times that of water, and water is 1,000 kilograms per cubic meter cubed. Force of gravity is 9.8 meters per second squared, and then our height is 4.2 inches. Okay, so 4.2 inches, and then 1 foot is 12 inches, and then 1 meter is 3.28 feet. Okay, feet cancel, inches cancel. We have a meter and a meter, so we have meters squared, kilograms, meter, cubic meter, and seconds squared. Alright, so these cancel, and we're left with kilogram per meter second squared, which is a Pascal. Pascal. Alright, so what does this come out to? If this is mercury, 4.2 inches of displacement of mercury is equal to how many pascals? 13,550 times 9.8 times 4.2 divided by 12 divided by 3.28. Okay, this comes out to 141.60. Well, 4170 pascals. All right. So for mercury in pascals, we find that this displacement is 14,170 pascals. Then, if we want to calculate this for what were the other things that we asked for? We asked for pascals, atmospheres, and psi, I think. So pascals, atmospheres, it's just a conversion. So pascals times 1 atmosphere per 101300 pascals. So this number divided by 101300, so that's 0.14. Okay, and if we want to know the psi, it would be 14.7 psi per atmosphere. So that would be times 14.7, and that gives us 2.06. So 2.06. All right, so that's the idea of what we do here. It's not very complicated. It's just application of hydrostatic pressure. And what we want you to do is we want you to do this for mercury, for water, and for tetrabromoacetylene. So 3 different chemicals or 3 different substances. And you'll find that the density makes all the difference. And so when you have mercury, that's a lot of pressure because mercury is so dense. It's a relatively large amount of pressure. If that was water, it's going to be 13.55 times less. I mean, it's all right here. If it was water, we would just not include this density factor. This is the density of water. And so for water, this is really quite easy. It would just be that 14,170 divided by 13.55. So it would be 1046 pascals divided by 101300 gives us atmosphere, so it would be 0.01 atmospheres and times 14.7 gives us psi, which is 0.15 psi. And now that you have it in water, you just see what the density is for tetrabromoacetylene, which I think is 2.55. I really should get myself organized here. Sorry, the density of tetrabromoacetylene is 2.97, 9655. So it's basically 2.97 times more dense than water. So for tetrabromoacetylene, it'll be these values times 2.9655. So I don't need to work that out for you, I don't believe. So this is the approach. Now let's see if I can find my camera buried under all this stuff and turn it off.